you want us to do now? The second thing you want us to do now is to be able to do what? We solve for the Reynolds number. So the Reynolds number now become what? Reynolds number become average velocity times hydraulic mean diameter over viscosity. And this value for this is equal to what? 2.097 times 10 to the power negative 5 meter per second, meter square per second. And this value for the hydraulic mean diameter we know is 0.2, and this average velocity is equal to what? 3.75 meter per second. Therefore, the Reynolds number becomes 35 comma 765 is a dimensionless value, and we can see that this is bigger than what? 10,000. And therefore we have a turbulent flow that is actually entering the pipe. And which pipe? The Dutch pipe. And because we have the turbulence flow, now for a Dutch, a flow that enters the pipe, entry flow, or you say the inlet flow should be characterized. How do you characterize that? The length for the hydraulic flow is compared with the length for the thickness of the pipe with respect to what? 10 times D is the formula, and that we have 10 times what is the diameter, which we calculated. We had 0.2 for the hydraulic mean diameter, which is actually this diameter we're talking about. And in that case, we have what? We have 2 meters. Then we can now, so that's how we characterize the flow for the inlet. We use the length for the pipe with respect to hydraulic pipe flow and thickness to get that flow parameters. But like I told you, that is just a characterization. It's not really important. You may ignore that section, you may not include it. It's not a big deal. But what you must never ignore is the Knudsen number, which is equal to what? The value for H, and in this case we're going to have the hydraulic mean diameter over K value. And for the selection of the Reynolds number, if you look on the book, we're going to have this condition for that particular flow: 0.023 Reynolds number, 0.8 Purdian number, 0.3. That is the process. But we know that this is 0.7154, and we know that this is equal to what? 35,765, and therefore if we put those values and simplify, the Knudsen number will become what? Will become 1.4. And therefore we come back to this expression. We solve for what? We solve for H. And what is that H? It is the convection heat transfer coefficient. It is the convection heat transfer coefficient, and therefore we use this formula and solve for that. If I use that formula, I'm going to have H is equal to what? H is going to be K over the hydraulic means diameter times the nozzle number. In that case, I'm going to have this, which I know was equal to what? Was equal to 1.4, and this is equal to what? The hydraulic mean diameter I know is 0.2, and this value for K is equal to what? 0.02953. So this value will be equal to what? 13.5 W meter square 10 degrees Celsius. That's the value which we are going to have for the convection heat transfer coefficient. And now, for us to finish this problem now, you may just want to be able to look at the area of cross-section. Area of cross-section for the system is equal to what? 4 times area times length. This is equal to what? This is equal to 0.2. This length is equal to what? 8 meter. So that will give me what? Cross-sectional area. From that formula, I'm going to have 6.4 meters square. Now, can I determine the mass flow rate for the system? Remember, we have the flow rate. Now we want to determine the mass flow rate. The mass flow rate for the system can become what? Density times the flow rate. So this is the flow rate. This is the mass flow rate. And if we look at this density, we know the value for density is equal to what? 0.994. The flow rate was equal to what? 0.15 cubic meter per second. So that mass flow rate will be equal to what? 0.150 kilogram per second. And therefore we can determine the exit temperature. We can determine the exit temperature. So T exit, which is equal to what? Exit temperature, which is the outlet temperature, is equal to what? Is equal to surface temperature minus surface temperature minus inlet temperature exponent negative H AS mass flow rate with respect to what? Specific capacity. So when you put those values, this, we know this as what? 1008, and this we've seen that to be what? 0.150 kilogram per second, and this was equal to what? 13.5, and the temperature for the inlet is equals to what? 80 degrees Celsius. Temperature for the surface is equal to what? 60 degree. So this is the inlet temperature. That's the inlet temperature, and this is the surface temperature or the surrounding temperature, and that's the exit temperature. So in that case, that temperature becomes what? Becomes 71.3 degrees Celsius. That is the exit temperature. Now, can we determine the exit temperature from the system, yes, this is the exit temperature. So the temperature exit for the system is equal to 1.3 degrees Celsius. That is the exit temperature. The last thing you want to talk about, remember we had to determine the exit temperature. We had to determine the exit temperature and the rate of heat loss from the Dutch due to Attis space. So now we want to determine the rate of heat loss for the system, and that can be determined using the log mean temperature difference. So from log mean temperature difference, which is equal to what? That is the log mean temperature difference. Log mean temperature difference into a C. That is the log mean temperature difference. It's a change of temperature. This is change of temperature. Change of temperature. This is log or lean function is equal to what? Is equal to, I want to space this out so you don't get confused because of my writing, equal to the temperature at the inlet minus the temperature at the exit over the lean with respect to what? Surface temperature minus temperature for the exit over temperature for the surface minus temperature for the inlet, I. So this is exit temperature, this is inlet temperature, this is inlet temperature, this is surrounding temperature, this is exit temperature. So make no mistake. So how do I get that log mean temperature difference, which is log mean temperature that is in lean? That is in lean. That is in lean. Your calculator has lean function. That will become what? That will become temperature at the inlet minus temperature at the exit over lean temperature for the surface minus temperature for the exit over temperature for the surface minus temperature for the inlet. So this is equal to what? 80. This is the one we calculated as 71.3. This 71.3. This is 80. This is 60. This is 60. So the answer here will become what? Negative 1.5. Negative 1.5.2 degrees Celsius. And can we calculate the rate of heat loss? So the rate of heat loss now. So this is the rate of heat loss is equal to what? Is equal to H AS change in temperature lean. And in that context now, you may see that we have, which is H AS so this is 13.5 5, this is 6.4, and this is negative 15.2, and this will give us one minus 1.313 watt. So that is how we use the log mean temperature difference to determine the rate of heat loss for air or water in a system, and that's how we utilize the log mean function for a Dutch pipe. So there are two kind of problem in this chapter. One is Dutch and one is not Dutch, and we need to know how and when we can use the average temperature, and when and how we can use the log mean temperature difference. And I've explained that it's only for a system that is undergoing isothermal process. So the system must be undergoing isothermal process. That is the only time we can apply this expression for the log mean difference. And in that case, we don't need the average temperature. So this is not needed. So please watch this video before coming to class on Monday. That is our class tomorrow. Watch this video before coming to class, because we're going to do one more problem and we work on our project. God bless you. Have a nice day. Bye-bye. Bye-bye.